Hi, good evening. So we start the lecture. So turn on video. Yeah, I gave comments on your final projects. If your presentation is on the first 2 days, I think the December 5th and December 7th. I haven't seen the late submissions yet, but you should have received the comments already in Canvas. So just check it. And especially a few students need to submit the plan again. So just make sure that your plan is okay or not. So basically, as long as your data is somewhat reasonable, I suggest something for revising plans. So if I say maybe you have to change the data set, probably that is because I think that the changing data is easier than develop something on the same plan. So most of the time, the resubmission is needed when the data set isn't really possible to analyze. So for example, the data set has already been summarized, so you cannot summarize it more. So that is the typical case that you need to resubmit. And for the presentation on the last day, I haven't commented on your presentations, your project plans. So probably I will comment by the end of this Thanksgiving weekend. Yeah. Any questions about project plan? So the PDF file is attached as my comments. So just read it if you have already got my comments. Okay, so today,
Good question.
oh yeah, sure.
I know I signed up for like a later day, but if possible, are we allowed to like move up in time? Like if I wanted to perform or I guess like
Or
present.
move up the date.
Yeah, is that possible or no?
Uh, as long as you can find another students who can change the date, then that's fine. But we cannot really add one more presentation. So yeah, I think that do you want to make the presentation in class or
Oh, I'm sorry.
some of the students have to make presentation in class and some of the students have to make a video. So
Oh, yeah. I would prefer to just do it in class.
in class, okay. So is there any students who want to change the date for a later date? Not really.
I can switch.
Oh, okay. So let me see. I will share the screen. Okay, you're just a moment. I think that this is the presentation list. So I think Alex, you said that
Yeah.
you will change. Okay, so maybe then Jason, when?
Oh wait, I think
Oh,
I'm in.
sorry. Oh, the same date. Oh, sorry. The 7th to 5th, you mean?
Yeah, I want to go to the fifth, but if it's not, it's no big deal if I can't. I was just asking.
Uh-huh. Okay. Does anyone wants to change between 5th and the 7th? No? Yeah, I think maybe I think the only 7 students. So yeah, you can make presentation on 7th. Do you have any um schedule on 7th or Jason?
No,
No.
I
Okay.
pretty much finished up, so that's why I thought it would take longer than it.
Okay, I see. Yeah, maybe we stick with the plan. So anyway,
Okay.
you can finish the slides first earlier, then you can just make presentation on 7th. So yeah. Okay. So that's it. And okay, so I will just check the who is. Yeah. Just a moment, sorry. Ryan, Jordan, Andrew, Rihanna, Neil, India. Okay, and I think I received several questions. No, one question. For some reason, I'm not seeing comments on my submission. I think I haven't commented on your project plan, Jose. I think that Jose, your presentation is on the last date, I think, no? Yeah, your presentation is the last date, so just be patient. A few more days I need. I'm also making comments on the project plan for another class, so just wait a few more days. Yep.
Understood. Thank you.
Yeah, thank you. Okay, so at first, I would like to discuss one data visualization example today, because it may be helpful for your final project. And after that, we will finish the chapter 11. Chapter 11, basically, we haven't discussed the, I think, the multi-collinearity. So some model diagnostics I haven't discussed. So we will discuss it. Then after that, we go to chapter 13. Maybe the first 1 or 2 sections of chapter 13. So that is about different type of regression model whose response is binary, either 0 or 1. Okay, so let's see the at first the data visualization example. I have to share the screen, so so this is just one graph I made, just not for this class, but just as my hobby. So this graph have basically the 3 pieces of information for each plot. So the x-axis is the price. Okay, so this graph is about the Honda car sales and the car price. And the x-axis is the minimum price of a car model. So for example, the Civic, the minimum price is about probably $27,000 or something, but I compare the price between countries, so I use just the Japanese yen as time unit, the unit. So this is about the it's about 3 million yen, the 3.5 million yen. And the y-axis is country. So this is Japan and this is US. So these are sold in Japan and these are sold in United States. But if I put all plots on the same line, the same horizontal line, the graph is too clouded. So I add artificial noise on y-axis, the y coordinates, so that for example, this circle and this circle are distinguished. Yeah, so the x-axis is price, the y-axis is country with some artificial noise, and the size of the plot is the size of sales. So this means the Civic and Accord and the CRV have almost the same size of the sales, maybe Civic slightly larger, HRV slightly smaller, the Civic Type R much smaller. So the area is proportional to the sales size. So this is just made by usual, the scatter plot function. And I want to discuss the code here. And the Honda sales data is on the website. So basically we only have 2 columns. I think the price, I think this, yes, 3 columns. So sorry, maybe I should say that there are 4 columns. So the first column is about the name of the car, the name of the models. And the second column is the price. And the third column is the sales figure. And the fourth column is either Japan or United States. So, and I read the data. This data is available on the website, so you can download from Canvas. It's available in CSV format and the zip format. And country is a factor, so I make it as a factor vector. So either the country column is either Japan or US. And the yeah, actually the first one, just you can ignore it. This is just box plot. And the here to here is the code for the graph I showed. So yeah, I said that I added the artificial noise on the country. So at first I set some random seed and I added noise on this the country variable. So country is either Japan or US, so either 1 or 2. Maybe 1 is Japan and 2 is United States, because basically it's alphabetical order. And I added the additional noise, artificial noise. So jitter function add artificial noise. So it's the same as the as numeric country, the plus maybe R norm of something. And the factor is the size of the noise. So I don't know what's the scale, but we can add this. Maybe like the standard deviation is the 0.1 if factor is 1 or something like that. So we added artificial noise. Then I saved the graph as a JPEG file. So in the final project, probably you have to save the file as some JPEG file or PNG file, or maybe other bitmap file. So the JPEG, then file name and some specification, width, height, and the point size. So this save the graph in your computer in the default working directly. So if you set working directly, I didn't have it here. In working directly, this file is saved as honda.jpg. And the device of is the end of this JPEG file. So between this line and this line, that you can write code for generating a graph. And this graph is basically just one plot. And the price is x-axis and the country is y-axis. And this is the CEX. CEX is the point size, basically the size of plot, size of each plot, each circle, each dot, each observation, I would say, each observation. So these observations are represented as a circle. So basically the radius of circle or the diameter of the circle is the CEX. And the default value is 1. So if you make it larger, then this number becomes larger. So the sales is, so then we want to make the area proportional. We want to make the area being proportional to sales. So I take the square root of sales so that the area is proportional to sales. And I multiply by some factor just to adjust the size of the plot. So first I just ignored this 0.02 and put the CEX is equal to square root of sales so that the graphs are really large. For example, the Civic is like this because it's a very large circle. So I want to make it smaller. So I want to make it the 50 times smaller. So I multiply some small number. And this is the y-axis is equal to nothing because I make it as a factor, then I make it as the numeric because we want to plot the country as just the place of 1 and the place of 2. So if we do nothing, basically this becomes 1 and this becomes 2, but this isn't very informative axis labels. So that I want to replace this 1, 2, and Japan and US. So at first I specified that I don't put anything. I do not put anything as y-axis. Then later I put the y-axis as the Japan and the US. So the 2 is the second dimension. So this means the y-axis, and the original numbers are 1, 2, but we replace it by the Japan and the United States. And the color is the 2 times the numeric country. So basically, the color is, okay, so 1 is black, and the 2 is red, and the 3 is green, and 4 is blue. So I just want to make it Japan as the red circles and the US sales as the blue circles. So that I want to make it 2 and 4. So just I multiply 2 by the country as numeric. So in this case, the 1 country is equal to 1 for Japan and the 2 for US. So if you multiply by 2, this becomes 2 and 4. So that becomes red and blue. And this is just X label and Y label and the range for Y. So 0.5 to 2.5. So again, so this is 1 and this is 2. And I added artificial noise. So I want to make it I want to make it starts at 0.5 and ends at the 2.5. Then the text, the price JPY, country J, negative 0.1 label. So this is basically the what's that? The text price JPY. Yeah, so this puts the these names, the model names, and the model names should be just below each circle. But if it's exactly on this place, then it's hard to read the title. So we want to make it a little below the center. So that's why I put -1 here. And this is the text label. So the model is like the CIVIC or RCode. So this is text information. So model is 1 column of the data set, so that we specify it so that these letters appear. So that is how to make this graph. And you don't really have to make all graphs fancy, but I want to discuss one example of data visualization. I got 2 questions. If you don't set seed, does it have a default seed that it uses? Yes, so yeah, that's a good question. So just I want to make it the graph somewhat reasonable. For example, just by chance that this circle and this circle are at the same place, it's not good. So I tried several different seeds and to make it the graph, to make graph look better. So that's why I set the seed, but you don't really have to set seed. Then every time the graph is slightly different. So this vertical location of these points are random every time. Yeah, a good question. Yeah. And another question I got, just a moment. Can we not take a screenshot of our graph to use in our final project slides? Screenshot, yeah, that's fine. That's fine. But if you save it as something, then the graph looks better in terms of resolution. So yeah, these days the computer has very high resolution, so it may be fine. But if you save it, then it looks better. So especially I make it the large JPEG file by the 1200 by 800. So probably this graph looks better than just screenshot the graph. But you can do that. And screenshot probably compared to the quality, the size of the file becomes a little larger. But yeah, you can do that. Yeah. Okay. Yeah, often when I write a paper with some other researchers, sometimes they ask me to make the resolution as high as possible. I forgot what's the maximum possible number, but yeah, you can make it a high resolution graph. But if you change the resolution, sometimes the balance becomes different. Maybe the ratio of the graph size and the letter size may change. So you have to adjust maybe this point size option to make it reasonable graph. Yeah, so that's one data visualization. Maybe it's good to have more visualization, but just one visualization here. Are you interested in if I make the data visualization class? No? I don't know. Maybe I should make some vote. Oh, yes, okay. That's great. Maybe the start 50/30 is so demanding, so maybe we should divide it into data description part and the maybe statistical analysis part in the future. Maybe you have already studied both in some way. Okay. Okay, so last time that we discussed multiple linear regression. So today I want to discuss one typical problem that multiple linear regression has. So that is the so-called multi-collinearity. So suppose that we have this multi-linear regression model, and suppose that this is by simulation, so that we know the coefficient of x is 1, x1 is 1, and the coefficient of x2 is also 1. So y is equal to 3 plus x1 plus x2. But suppose that the x1 and x2 are very highly correlated. So we think about that situation. So in such a case, if we generate data for y and x1 and x2 for maybe 1,100 observations, and estimate the parameter for x1 and x2, we can probably see problem to identify these coefficients, because if x1 and x2 are very similar, the correlation is very high, then x1 and x2 are almost the same. So that means the x1 plus x2 is almost equal to 2 times x1, because x1 plus x2 is, almost equal to x1 plus x2, right? x1 plus x1. And also this is very close to 2 times x2. Or maybe we can also say that there may be 3 times x1 minus x2, and so on. So we should have trouble to identify these coefficients. So we want to see what's happening here. So I just simulated some data. So x1 here. So actually the sample size is 50 here. And we define x2 as x1 plus small noise. So that means the x2 is similar to x1. So x1, the standard deviation of x1 is about 1, because this is the standard normal random variable. Okay, and I add just a small noise, 0.3 times the new noise. So the x2 is mostly determined by x1. And actually the correlation between x1 and x2 is 0.95. This is very typical, correlation if you choose similar variables. Even higher one is possible. For example, we have several stock market index. For example, the S&P 500, and another one is maybe Dow Jones Total Stock Market Index. The stock market return for those two indexes has correlation of 0.99. So the even higher correlation is abundant in the real world. And we generate y as the 3 times x1 plus x2 plus random noise. And now our objective is from generated y and x1 and x2, we estimate the coefficient for x1 and the coefficient for x2. And this is the result. And this should be 1. The coefficient of x1 should be 1, but the estimated as 0.7. And the coefficient of x2 is also similar to 1, should be equal to 1, but the estimated one is 0.93. And yeah, it looks fine because the standard deviation is 0.5. So maybe the true parameter is the estimate plus minus 1 standard deviation. So that's fine. But these t-values are pretty low. So these are not really statistically significant. So when we have the true model and we have the 50 independent sample, then we expect that these parameters, they should be at least significantly different from 0 because the truth is 1. Even we fit the true model with 50 observations, still the estimate isn't really statistically significant. So that isn't really good. So the problem happens because the x1 and x2 are very similar variables, and it's hard to distinguish. And yeah, even though this is not statistically significant result, we have some indication that it worked well. For example, the F statistic. So this model, this test statistic tests the null hypothesis that the y is just the randomly determined. So y is some random noise plus some the mean level against the y depends on x1 and x2. So for this test, actually the p-value is really small. So overall, this model is much useful than the null model. So it's a good indication that x1 and x2 are useful. And also the multiple R squared and adjusted R squared, that is 0.68 and 0.67. So that means about 2/3 of variation in y is explained by x1 and x2, just 2 variables. So that is a good indication that the x1 and x2 are useful, but still the parameters are not accurately estimated, so that these p-values are less than more than 0.05. And this problem does not happen when we only use one variable in a regression model. We regress y on x1. If we regress y only on x1, then the estimated parameter is here. So this is about the summation of 2 coefficients in the previous output. Previous output, the coefficients are 0.72 and 0.9394 maybe. So this is approximately equal to 0.72 plus 0.94, right? So the estimation result is not much different, but here standard deviation of the estimate is very small, and the p-value is very small. So we can say that x1 definitely is a significant factor to determine determine y. And also the same thing for y. So if we fit y on x2 only, then the coefficient of x2 is again very similar to the summation of these 2 coefficients. So 1.61 and here 1.62. So anyway, similar. And again, the standard deviation gets smaller and the p-value is very small. So it's very significant. So it sounds like the first regression does not work well because the both p-values are not small. But not necessarily the first regression is bad, because if we see, for example, adjusted R-square value, that is the 0.659, about 0.66, and here 0.65. But if we use the both predictors, that becomes almost 0.67. So overall, the fit is better. But only the problem is that these parameters are not correctly identified, not accurately identified. So that is the problem of multi-collinearity. So the true model is here, but this is worse than this simpler model? Not necessarily, because, for example, our adjusted R-square is actually better for the true model, higher for true model. So there is no problem to use the multiple linear regression even when x1 to xp are highly dependent. But the problem is just the standard deviation, standard error of the beta 1 to beta p becomes large and making it harder to test parameters. So often testing parameters is more important than the prediction. For example, think about the economists, that whether the inflation affects the real GDP growth or something. Real GDP growth means the adjusted for inflation. So when the inflation is higher, basically the more uncertainty, there is more uncertainty about investment. So the company invests less, so the growth rate in the long run gets lower. So that is the economic theory. So the economists, for example, want to regress real GDP growth on several variables. So such as, the inflation and I don't know, that trade surplus and something like that, and want to see if the inflation really matters for real GDP. So the coefficient of inflation is significant to explain, real GDP. So the significance is important. So, but if the multi-collinearity happens, then we have trouble to estimate and we have trouble to test that coefficient. Yeah. So we don't have any, the perfect solution for multi-collinearity, but at least this phenomenon happens. So you shouldn't be surprised if some useful variable have the insignificant p-values. Yeah, in the past, one student fit the y on I think about 12 different predictors, and they worry that all predictors are insignificant. All p-values are larger than 0.2 or something. And just I handpicked the 3 or 4 variables, and I fit y on those 4 variables, then all variables becomes very significant. So, and he was surprised, but that is the typical situation of multi-collinearity. Yes. Yeah, and the variance inflation factor in R to check for multi-collinearity. Yes. So the VIF function, the variance inflation factor function. So the variance inflation factor. So this is basically the ratio of standard deviation of this x2 and this number. So the standard deviation when all predictors are included. And if this ratio is very large, then like more than 10, then maybe you have to worry about the multi-collinearity. Yeah. So you can check if the multi-collinearity happened. Yeah. Yeah, you can check it, but yeah. Anyway, so this is the intrinsic problem in multilinear. So the multiple linear regression, so that you cannot really solve it, but at least you can see whether a problem happened or not. Okay, so that is chapter 11 and exercise. Yeah, so for house price data, so remember that we have analyzed house price data earlier in this chapter, the house price data. We have probably 4 variables: the price, the square foot, and the year, and the number of bedrooms and number of bathrooms. And yeah, it's almost clear that the all 4 are useful predictors, but we can check if this is really the best combination. Maybe the dropping one variable becomes better. You can check with the AIC values. So maybe we do this exercise 1. So for house price data, they confirm that the full model is the best model by using the step function. And also the make a list of AIC values for all possible combination of predictors by writing a function. And yeah. So maybe we want to discuss this now. Before, yeah. Okay, maybe I will check the attendance first. Okay. And I share the screen. Okay. And I have the data set property cells here. So this is the data set for the chapter 11 earlier slides. So we have some, this is the date in some format, probably. Yeah, I think this is almost does not make sense, but yeah, we don't really use this one. So price of the house and the style actually is of the house, and the square footage and the year, the number of bedrooms and the number of bathrooms. Yeah. Yeah, and we want to regress this price on these 4 variables. So that is what we want to do. And we are doing it in this specific directly. So just I want to start our session. And we want to set the directly. So usually it's good to get directly first and then set directly. And I'm using this folder. Okay. So if nothing appeared, then you set directly, working directly correctly. So if you make some mistake, then this error message appears. Anyway, so then we want to read the data. So read the table. The name of the file is, I think, the property cells. So property cells.csv, and the first column, or the first row is the header. So header is equal to true, and this is separated by comma. So this, and you can check the structure of the data. So the date and the price and the style, square footage, year, bed, and best. And yeah, I just use this number of bedrooms and number of bathrooms as the numeric variables for this question. So at first, you can set the regression model, maybe full model, LMF. This is full model. As price, or maybe I yeah, maybe attach this data set first, and the price on these 4 variables. So the square footage and the year and the bedrooms and the bathroom. We have some trouble. Data plus. Then we can get the summary of LMF by this. Okay, so we have all significant variables. So we can use the step function to see if this is the best model. And actually, this is the best model, because if we drop this variable, then AIC gets worse. AIC is smaller if the model is better. So if we drop any of these 4 predictors, the AIC gets worse. So that means the full model is the best. So this is the final model. We can do the forward selection. So we can see help of the step function. You can see that we have the option direction. So the default option is both direction. So we drop one variable or add one variable at that time. But the direction forward makes the forward direction. And probably forward, we have to specify the starting model. So probably this does not really work, but maybe we can try that. Direction forward. Oh, actually, yeah, actually, this is the starting model, so that does not work. So maybe we have to fit the null model that is the LM, the y on y on one, y on one, y not y, the price on one. So this is the smallest model, and the LMF is largest model, and we have to set the scope of the model. So I think that we have to step LM0. We have to specify the smallest model, and the scope is, I think, the LM0 and LMF. I can check the format, the scope. Scope. Yeah, the range of models examined. This should be either the single formula or at least it contains the upper and lower, maybe both formula, maybe. Probably this way. Direction, scope, upper and lower. Yeah, I think the step function. I think that this is the scope data. We try scope is equal to LMF, maybe. No, it does not become larger. Forward selection, forward. The direction is forward. Sorry. Maybe list of two models. Yeah, this way. Yeah, okay. So if you specify the smallest model here and the largest model here, and we specify the starting model and the direction forward, then it starts with the null model. So price on just intercept. Then if we add one variable, then AIC value changes. So the baseline, if we think about the baseline, the intercept model have the AIC of the 11,254. But if we add square footage, then AIC value improved most by almost 800. So that we add square footage first. Then next one, after we add square footage, we add additional variable. And if we add year, then AIC improved the most. And the bed and bath also it improves, but the adding year, the improve the situation most. Then next, the price on square footage and year, and even the additional variable that makes it better. So we add bed. Then after that we add bath. So basically, yeah, so this procedure tried all of these models. We have the null model, and we have 4 additional models here, and 3 additional models here, and 2 additional and 1 additional. So this model basically this procedure step function checked the all 11 models and concluded that finally the full model is the best, even with the forward selection. if we don't want to see these intermediate steps, then we can specify the option trace is equal to 0. Then, oh, sorry, what's that? Trace is equal to 0. Then you can immediately the final result without seeing the intermediate steps. So that may be useful if you want to create the R Markdown file. Yeah, so this is how the step function works. Maybe some other options, the direction. Yeah. Probably the scale option changed the scale of predictors. They normalized the scale of predictors. No, the normalized AIC statistic. So yeah, you can largely ignore that. Yeah. Yeah, and the next one, next question of this one is that, yeah, sometimes you want to try all combinations. Probably you would not, but just I want to discuss how to do it. So we want to make a list of AIC values for all possible combination of predictors. That means the 2 to the 4th power. So we have 4 possible predictors. So in total, we have the 16 combinations, 2 to the 4 combinations. So writing functions. So we want to make a list of AICs. I don't know what's the best way to do that, but maybe, okay, so we can write some code. So we want to fit the model. So yeah, I think it's not really easy to do that, but we have the 4 possible variables. So so we have 4 variables, and we want to use these 4 variables. And these 4 are actually the 4th and 7th column of this data set. So that we want to select all combinations of these 4 columns. So the D47 is the data we want to use, right? So these ones. So maybe just we made it as X. And basically we want to try the regression such as the price on X of maybe, the first variable and the last variable or something like that. Sorry. Sorry. X price, define columns. Oh yeah, actually this is 1 and 4. Sorry. Sorry. Yeah, sorry. We want to extract the 4th and the 7th column and as X, and we want to regress something like this. So X has 4 columns. So price 490 observations, and the X14 drop levels. It looks strange. Okay, so X maybe 125, D14. I don't know why it does not work. Price on maybe just X1 we try, and LM. Yeah, it worked. And if this is 1 and 4, it does not work. Right, it does not work. Right, sounds strange. Yeah, we have 4 variables, so maybe we have to try in this way. So x first column and x second column, something like that. Then it worked. Yeah, I think it's a little hard to 1, 2, 2. That does not work. As matrix, maybe no. I think some problem about x. X is data frame, and the first and second cannot be extracted. So yeah. Yeah, if we want to try all combinations, probably we have to use the matrix. So yeah, maybe we have to make this as matrix. Then yeah, maybe that's fine. So we don't really have to use here, but yeah, we try all combinations here. So maybe we specify the index for predictor. Maybe this as originally numeric 0, maybe. Then we add numeric predictor. So maybe we set I1 in okay, so yeah, we have to make the all possible combination of predictors here. So we want to make this vector in some way. So okay, so maybe one possible way is yeah, so at first we make the 0, 1, 0, 1, 0, 1. So I1. I don't know what's the best way. We have 2 choices, whether we choose the x1 or not. So maybe for I1 is equal to 0 to 1, then IP, it may not be the best. So I1 is equal to 1, then we add we add 1. And if I2 is equal to 1, we add I2 as well. The second column as well, and so on. So I2, I3, and I4. Then we add 3 and 4, and maybe we use the for loop 4 times to see to make all combinations of these 4 predictors. Then for each case that we have to save the AIC of the model. So for each case, we want to fit the price on the specified column of X, so the IP. And as matrix, we need. This is maybe object of LM, and then we calculate AIC of LM, and we save it as maybe the list of AIC. So maybe we have, in total, we have 16 possible models. So we have 16, and we have to save maybe I1 value to I4 value and 5. So maybe we can like make like this, and we want to save the AIC value as the maybe the last column of last row of this last column of this M. So maybe we do like this. So that this is the matrix to store all AIC values for 60 models, and then this is the basic ones, and the basically yeah, and maybe we name the columns, call names of M as maybe whether or not square footage is included, and the year is included, and the number of batteries included, and the number of buses included. And finally, we get the AIC. Then we get this one, and then we specify, okay, so 1, 2, 3, 4. I1 and I2. And I3 and I4. Then we have to fill the row one by one. So maybe that we have to specify the j is equal to 1. So at first j is equal to 1, and that we fill in this way j, and this should be done within this for loop. So this should be done here, and the specify j. Then finally we have to add j to j plus 1. Not sure if it works, but we try this. Maybe it makes some error. Subscript I J1 M is 5 columns. Okay, so and the j plus 1, and the j is equal to 1, and the 0, 1, and the I1, I2, I3, I4. So yeah, that sounds fine. Okay, so just try what's j. J is 1. It stopped first. So mj 1, 2, 3, 4, 5, and the j is equal to 1. So it sounds fine. AP, okay, so LM, what is LM? LM does not work, so it stops before that. So LM as matrix. So what is IP? IP is 0. So IP is not updated. What is I1, I2, I3? Okay, so it stopped in the very early stage. So IP, I1. Maybe this does not work. It worked. I don't know what happened. So for loop, the one for loop, 1, 2, 3, 4, 0, 0, 0, 0, 0, 0, 0, 0. And the I1, I2, I3, I4, that is fine. And the AIC value is fine. And yeah, it looks fine. Sorry, I just want to make a list of AIC table, and I1, I2, I3, I4. 1 is all 0, then all 0, then probably it makes error. So sorry. Maybe I is equal to, yeah, if everything is 0, then we have some trouble. So I think that we have to modify this code. So if the everything is 0, that's a problem. So if the everything is 0, that means the product is not product. If everything is 0, everything is 0 means that maybe summation, maybe I1 plus I2 plus I3 plus I4 is 0, then that's a problem. So if more than 0, then this. Then if not, if 0. Maybe else statement here, then we fit the just price on 1. So probably this is the problem. So y. Okay, so then probably it works. J is equal to 1. Then M. Then you can see the list of AIC tables. It still does not work. It looks it worked for the first 3, but after that it does not work. I don't know why. 1, 1, 1, 1, and the 1, 0, 1. This works fine as well, but the 1, 1. Square footage and bed, I think it shouldn't be the same as this one. Why this happened? The 0, 0, 0, 1. So all combinations are covered from the line 1 to 16, so that should be fine, but the AIC value isn't really correct. And the LM, the as matrix IP, what's the last state of IP? Oh, I see. IP is not cleared yet, so that is the problem. So IP is here, and here, and then at last stage that we have to clear IP. So IP is numeric 0. Maybe this is the reason. Then we got the list of all AICs here, and the still AIC of full model is here. So yeah, I think it's the smallest. So you can see the whole list of the models. So if, for example, the line for only square footage and the ear are included in the model, the AIC value is the 11,809. But if we include the everything, 1 means that this variable is included. So that this becomes the 11797. So you can see this is the smallest. Maybe which mean of the M5, then you can see the 15th column is has the smallest, the AIC value. Yeah. So we now tried all combinations. So this becomes more complicated if we have some factor variables. Yeah, so we are not sure that it improves the situation or not. Yeah, certainly we can try. There's some variables like the yeah, we can make it the okay, so detach D, and the we can, for example, make the number of bedrooms as the factor variable, as factor of the D bed, and also the number of bathrooms, we can make it as a factor. Then we have the data set D with these factors, and we can set, for example, step of LM1. So okay, attach of D again. Sorry, yeah. Then step LMF, maybe LMF we have to learn again. So maybe we have to say the LMF is the full model. Full model is LM of price on these 4 variables for bed and bath and square footage and year. Then LMF we can run, then we can do step function and do that, and then we get this, and maybe AIC of this LMF. Actually this gets probably smaller, 11,767. So that is actually the lower than this. So actually if we make the number of bedrooms and bathrooms as factor variables, then result gets even better. You can get the summary of LMF also. Yeah, you get this. Yeah, in this way, you can analyze data for all models, but it's a little complicated. I got some questions. So for example, on our projects, so sorry. So for example, on our projects, if we get each predictor is insignificant, should we just regress them in groups of the 3 or 4 variables to show that p-values that indicate significance, and then keep the larger number of larger number of variables model? Yeah, actually, there is no solutions when the multiple collinearity happened. So as a prediction model, just include the many variables as long as for example, AIC improves. And to show significance is different issue. So yeah, you can do maybe simple linear regression for each predictor and to see which variables are significant as a single predictor. Yeah. And sometimes it makes sense that if we have multiple regression model with a few variables and all variables are significant, then that is maybe stronger result. Even if another variable is already in the model, still this variable is significant or something like that. Yeah. So the objectives are different. So we cannot really see the one size fits all answer, but yeah. So for prediction purpose, just include variables as long as AIC improves. And to show significance, it depends on the case. Maybe you want to try a single predictor, or you want to try the multiple predictors. Yeah. For example, if your question is whether year built has significant information, even if square footage is known, then you have to put both square footage and year to see the result. Another question: what does which mean means? Which minimum means? Which mean returns the location of minimum. So, for example, if we have X variable, maybe just random sequence, then this second two is the smallest. That is the fourth element of X. So which min of X returns 4. Yeah. So the fourth element is smallest. Yeah. Okay, so that's it for chapter 11. Sorry, maybe I spent too much time on this, but yeah, I think that it's at least good for coding practice. So basically, trying all combination is complicated. If everything is numeric variable, maybe you can use this code, but otherwise, it may be more complicated. So you cannot put factor variable in the setting because I make this as matrix. But if we have factor variable, we cannot make it as numeric matrix. So this works only for numeric variables. Okay, so that is fine. Yep. And the data, yeah, find the data set on the internet which have multi-collinearity. Yeah, many. For example, if you have the two different definition of unemployment rates, those are highly correlated. Yeah. Or if you regress the SP500 data on maybe Apple's stock and the Microsoft stock, then Apple's stock price and Microsoft's stock price are highly correlated. So they have multi-collinearity. Yep. Okay, so now we go to chapter 13. I think we don't have much time, but still maybe we can discuss the introduction. Chapter 13. Do you have any other questions so far? Okay. So chapter 13 is logistic regression. So main difference between usual regression and logistic regression is in response variable. So if the predictor X is continuous and the response is continuous, and then we can use the linear regression model. So predictor is the categorical, and the response is continuous. Then you can use the ANOVA. And ANOVA is actually the special case of linear regression. So we can say still that you can use linear regression. But the problem happens when predictor is continuous and the response is categorical. So this is a difficult case, but the categorical, if only 0, 1 binary, then we can use logistic regression. So this is the difference between logistic regression and the linear regression. So response variable is binary. Yeah, and these slides basically cover chapter 13 of the textbook, but the sections of the textbook are not in the same order of the discussion in this slide. Okay, so suppose that the Y is either 0 or 1. So typically in the medical data, 0 is benign and 1 is malignant. Or maybe marketing data, 0 is unsuccessful and 1 is successful, or something like that. And we have X values. We have the P different variables plus intercept. So basically we want to do this. So Y is binary, but still we want to think about this. But this does not make sense because for some value of x1 to xp, maybe this value of x beta exceeds 1. That does not make any sense, right? So if this becomes 1.5, then Y is either 0 or 1. So this prediction is really bad. This explanation is really bad. So we should have the something between 0 and 1 as the fitted value. So we have to modify this model somehow. Well, mathematically speaking, with this model, the epsilon cannot be a normal distribution, because if Y is either 0 or 1, we only have the 2 possible values of epsilon. If x beta is, for example, 0.9, epsilon is either 0.1 or negative 0.9, right? If Y is 1, Y is 1, and if Y is 0. So the normality assumption cannot be satisfied. So we have some trouble. The fitted value does not range from 0 to 1, and also epsilon is not normal. So how to make Y continuous? That is one problem. So if binary, the possible error values are only 2. There are only 2 possible error values. So we want to make left-hand side as continuous variable. And the trick is here. So we think about the probability that Y is equal to 1. So given X value, what's the probability of Y is equal to 1? So that is maybe the given maybe weight and the height and the BMI. What's the probability that that person has specific disease? So that is the probability of Y is equal to 1. That is also the equal to expectation of Y. And that we represent this as Y, this as pi, and that we consider the model that the pi is equal to the linear combination of x1 to xp, and yeah, x1 to xp. And pi is already expectation, so we don't have any error term, but we want to express pi as a function of x1 to xp. So this is the first first trick in the logistic regression. So the left-hand side is an expectation. So that's the case. So even if the linear model, we are doing the same thing. So Y is equal to beta naught plus beta 1x plus epsilon. If we take expectation of Y is equal to beta 0 plus beta 1x. Expectation of epsilon is 0. So if we take expectation, the error term disappears. And the more serious problem is that this right-hand side may not range from 0 to 1. If we change x1 values, then the right-hand side, this entire quantity can exceed 1 or exceed the below 0. So that is a problem. So we just make a transformation of this probability to make it to make the pi ranges from the negative infinity to positive infinity. So we think about the function from 0, 1 to r. So we think about the function between 0, 1 to r. So we think about this kind of curve. Oh, sorry, like this kind of curve, so that for transformed version of probability, it ranges from negative infinity to positive infinity. So that is another trick. And with these tricks, that we can make the so-called logistic regression model. So this is the function f, and the f of the success probability expectation of y is equal to the linear combination of x1 to xp. So this is the idea of logistic regression. And in general, this is a special case of so-called the generalized linear model. So we have this so-called link function f. And after we fit the model and estimated the model, we can get the probability of y is equal to 1 as f inverse of the x beta. So that is the idea of the logistic regression model. Okay, so we discussed more details about logistic regression next time. Okay, do you have any questions? Okay, so if not, see you on next Monday. So have a happy Thanksgiving.